The third of the formulas for telescopes is resolution or resolving power. Looking at the formula sheet, the formula for resolution is right here. It actually says angular resolution in arc seconds or seconds of arc is equal to the number 5 divided by the diameter of the main optics of the telescope in inches. And remember that the diameter of the main optics doesn't matter whether it's a lens or a mirror, and that's what we call the aperture. So just like the light gathering power of a telescope depends on the aperture, so does the angular resolution. And bigger is better. You can't get away from that with resolution. So resolution is the ability to see fine detail. For example, if you were looking at a double star, two stars that are very close to each other or appear very close to each other in the sky, you want to be able to see the fact that there are two stars, right? One star, two stars. You don't want to see one smushed blob. So this is bad, this is good. And the ability to be able to see that depends upon the aperture of the telescope. So essentially what you are doing is you are comparing how close could these two stars appear to be to each other and still be able to be seen as two stars and not one blob. So what you normally will do is you will calculate the theoretical angular resolution of a telescope, and then you will say, given the following scenario, like the size of a feature on a planet or a separation between the two stars in a double star system, and that's given as the distance between the centers of those two stars, at least what it appears like. And then you'll say, can this telescope see things that small or not? Before we get to the example, I want to point out that this is a theoretical value. This is if you had a perfect telescope under perfect conditions and if the atmosphere of the Earth didn't interfere. So here is a common example. Can a 4-inch telescope separate a double star of angular separation 0.75 seconds of arc? Can an 8-inch do it? Well, for each telescope, you need to calculate the angular resolution. And the angular resolution is the number 5 divided by the aperture in inches. So you'll notice that the aperture is given in inches. So very simple, you just take, for the 4-inch telescope, the number 5, divide it by 4, and you end up with an angular resolution of 1.25 seconds of arc. This is the smallest angular size that this telescope can see. It can only see things this small and bigger, okay? So you are given a double star where the two stars appear so close together that their angular separation is only 3/4 of a second of arc. Your telescope can hypothetically see down to this. The separation of those two stars is smaller than the smallest angle the telescope can see. So that double star will appear as one fuzzy blob. You cannot separate it. Well, what about the 8-inch? Well, we divide the number 5 by 8. We end up with 0.625 seconds of arc. That is the smallest angular size that telescope can see. It can see that big and bigger. So you are again given a double star where the apparent angular separation of the two stars is 0.75 seconds of arc. 0.75 seconds of arc is bigger than the smallest angle the telescope can see. It can see things 0.625 and bigger. So yes, you will actually, at least hypothetically, see two separate stars. Here's another example. What is the angular size of the smallest feature on Mars a 10-inch telescope can see? So to find the smallest, at least hypothetically, the smallest angular size that your telescope can see, you need to calculate the angular resolution. The angular resolution is the number 5 divided by the diameter or aperture in inches. You are given a 10-inch telescope. So the number 5 divided by 10 is 0.5. It can see features as small as 0.5 seconds of arc. So could this telescope theoretically see features of an angular size of 1 second of arc? Well, let's compare it to the minimum, the smallest angular feature the telescope can see. The telescope can see things as small as a half a second of arc. 1 is bigger than 1/2. So yes, you can see features this small on Mars with this telescope. Could it see features with an angular size of a 1/3 second of arc, 0.333? No, because 0.333 is smaller than the smallest angle the telescope can see. So you cannot see features that small with this telescope. So when you're observing through a telescope, you obviously want to be able to see the finest detail you possibly can. You want to see the smallest detail. You want to have the best angular resolution. And remember, best angular resolution means being able to see the smallest detail. But since the angular resolution is inversely proportional to diameter, because diameter is in the bottom of the equation, in order to be able to have a good angular resolution and see very tiny angles, you need to have a very big number down here in the denominator. So a bigger telescope will allow you to see smaller details. That is why you want a big telescope.